Okay, right, so this is going to be feedback for the 2017 Practical Geochemistry and Data Analysis exam. So this is just going to be on the stable isotope questions. If you want some feedback on the radiogenic isotope and general element partitioning question, then you should come to the feedback session and Jeff will give you some feedback, I guess. So just quickly, we're going to go over a couple of both of the questions. But before we do that, just some general advice on exams and stuff to do with those exams. So right, so if we look, just I guess advice as it would be for any other exam: revise early, use past questions. They're quite helpful. But they're not always going to be an exact replica of what we're going to see in the exam. So we do tend to write new and exciting questions every now and then. So what you can do to try and prepare yourself is you can look at some past questions, but also try and go through the content of the course and try and think of some of your own questions. Try and identify what is it that in each kind of part of the course are the key things that we're trying to get across, and think about writing your own questions for those. We did that in a kind of a practical, which I guess some of you came to, which was fun. You can always ask me or Jeff about parts of the course and whether this question that you've come up with is a suitable summary of the subject material and is the kind of thing that we're expecting you to be able to respond to. Okay, so this clicker's not working terribly well. So again, general advice. So now, particularly at the honours level, we are looking for you to expand a little bit more on what might be just the obvious answer to a question, provide a little bit more detail, and provide some evidence that you are reading around the subject, so you're not just kind of coming to the lectures, or at least you are coming to the lectures. Some of you that didn't come to the lectures, obviously, it'd be good if you came to the lectures, but fun times I'm sure you were having. But we are looking for you to actually add a little bit more to your answers than just what might be just the seemingly obvious. And I'll give you an example of that in perhaps the first question we look at. It is important, though, that you do stay relevant to the question, so you don't kind of go off into some kind of like crazy tangent of some niche knowledge that you've gathered from somewhere without specifically answering the question that we've asked. And that's really important. So making sure you're doing what we ask you, but then also providing extra details is really good. Okay. So again, think about rewriting questions in your own words to make sure you understand what we're asking. And hopefully, going through videos like this one will help you understand a little bit more about what we mean when we're asking some of these questions. Okay, so just a quick overview. This is just the mark summary for this year's exam, unmoderated as of yet, so this is subject to change. So this is just the mark distributions for questions 1 and 3. And you can see quite a broad range. So some people did very well, and some people could have done a little bit better. But I guess doing quite happy with the mark distribution. Some of you clearly are really engaged in the subject and have learnt something. Maybe you knew it already. Who knows? But really, some really good marks towards top end up here. I like to think that doing well in one of my exams can be considered an achievement. We don't just give out marks willy-nilly. But there you go. So those of you did well, well done. Those of you did less well, hopefully this video will provide some insight into where you could have done better. Just a little bit of I guess, again, nagging some of you maybe that you're not revising during the course and you're waiting till the end. So this is some of the YouTube stats from the UK users of the videos that I post online. So this includes the first year content. So these peaks here are the first years when I said, hey, first year, go watch this video. I think this might be you, and obviously not very many of you were actually watching that particular introductory video when I told you to. But the real thing is these peaks over here, where I can see that at this time, just before the exam, which was on this day here, this is when you were watching the videos about what's going to be in the exam, the exam feedback videos from previous years, when you really should have been looking at those a lot earlier throughout the course. Because if you do that, you can kind of get an idea earlier on whether there are gaps in your knowledge, whether there are your approach to how these questions should be answered needs to be addressed. Whereas if you're doing this at the last, within the week before the exam here, it's almost a guarantee of bad times for you. So actually, just before we move on to the questions here, so I'll just flip back to this, give you focus on something somewhat depressing for some of you, but reassuringly excellent for the rest of you. Thinking about checking your answers to questions. So this wasn't really an issue for my questions, more for Jeff's questions, but particularly when you're asked to do a question with calculation in it. So for example, if one of the questions on the exam was to take in some data in an isotope and calculate the age of a rock, well, you should always check that answer to see if it's reasonable. And there are a number of people that went through, did some calculation, came up with an answer, and that answer was either older than the age of the solar system or younger than a year. And you should know that both of those scenarios are not really geologically feasible for the formation of a crystalline rock. Okay, so you should always, even if you can't figure out where you've gone wrong, if you know that you've got the wrong answer, you should write down that you have the wrong answer, because then you can do something about, well, at least we can give you some credit for realizing that this is clearly wrong. Okay, so in addition to things like having the right numbers of significant figures and giving the right units and all that kind of stuff, but if you're giving a numerical answer, do check that it is physically plausible. Okay, so you're not kind of calculating a mass that's kind of bigger than the sun, or the ages that are kind of outside the realms of geological possibility. Anyway, so that aside, the stable isotope questions for this exam. So just going to go through these in sequence. So there was one question which was about how isotope ratios are measured, and why we use standards, and how isotopes fractionate. And then the other question was about how boron isotopes are used as a proxy for pH. But actually, the question is a little bit more nuanced than that, and we'll come on to that in I guess the second part of this video when we get on to that question. Okay, so looking at the first question, again, 3 parts. It's always a good idea to have a look at the mark kind of allocation for those kind of, when you have it split into 3 parts. So it's clear that part C is where most of the marks are being allocated, and quite a lot of people did very well in parts A and B, but then fell over slightly. We're not giving a really full description in part C. We're missing out on the mega marks. So first of all, why are standards used when measuring and reporting isotope ratios or isotope compositions of samples? There are a number of reasons we do this. I guess first of all, that the ratios that we actually exist in nature tends to be quite extreme. Okay, so there tends to be lots of one isotope and very little of another. So you tend to get ratios that are very, either very, very big or very, very small, depending on how you think about how your ratio works. Is it an uppy-downy or a downy-uppy? But basically, one of the reasons we use standards is because the ratios are very extreme, and that makes them difficult to measure the absolute values of them. Okay, so when you measure in some mass spectrometer, you put some ions into one side of the mass spectrometer, and the other side you collect the different isotopes in different collectors, maybe over the other side. It's very difficult to measure an absolute ratio, particularly when the sizes of these isotope beams are very, very different. Okay, so one of the reasons we use standards is because the ratios are hard to measure in their absolute terms. So we can measure the ratio of a sample and a standard, and we can look at the difference in ratios between the two and effectively use that as the measurement, which is much easier to make than the absolute isotope ratio. Another reason is the measurements that are made in different laboratories around the world might give slightly different kind of values, because when you put in one side of an instrument, you put in a sample, maybe not all of those ions will get to the other side, and that efficiency of transmission through your instrument might be different for different isotopes, which is annoying. That means the ratio that you end up measuring is not the ratio in your sample, and that may be a fractionation that's laboratory specific or method specific. So if we have standards which are the same isotope composition in every little pot of standard that we hand out to different labs around the world, we can compare between the two. So inter-lab comparison is a really important reason, again, why we measure isotope standards. Okay, so those are important things that should be in that. So again, there's a kind of a simple answer, hard to measure absolute values, but we can also add in details to questions with additional reasons why we need to use standards. So here are some of the examples of standards. You could have given some of the examples in that question. It's not specifically asking for them, but you would have got credit, I guess, extra additional bonus super credit if you'd have given some examples as we do that. Okay. Likewise, you could have put those examples in this part of the question. Wouldn't really matter. We'd have fudged the marks around and given you some credit for relevant additional information. But the second part of the question, part 1b, is basically how are the isotope ratios reported relative to these standards. Okay. So what we're really looking for is you to be able to kind of spout out this equation where we have the kind of the delta notation reported as the ratio of the measured isotope ratio in the sample over the measured isotope ratio in the standard, minus 1 times 1,000. And then you could also add in some little bit of details about why we have the times 1,000, and that's because the variability in isotope ratios in nature is typically very small. Okay, so this is why we have this notation. Again, you could have had a little bit of extra super bonus credit if you'd have said sometimes we use epsilon instead of delta when we have even smaller isotope ratio variability. But then again, it wouldn't be essential to get kind of the marks. Okay, so now we're going to move on to the last part of this question. So explain the isotope fractionation mechanisms that lead to polar ice sheets to have oxygen isotope compositions that are up to 50 parts per thousand or per mil, lighter than ocean water. Okay, so there are a number of kind of things in this question. So basically, first of all, again, rewriting it, kind of see if we can think of expressing it in our own words to identify different parts of the question. Why are ice sheets isotopically light? Okay, that's kind of okay. Another thing we can say is, well, there's going to be some isotope fractionation associated with this reason why isotopes are isotopically light. So this question kind of could also include in the answer, how do those isotopes fractionate? Okay, we're looking for the fractionation mechanisms in the question. So you could say, why are isotopes isotopically light? How do isotopes fractionate? And then more specifically, we could actually kind of try and narrow this down. So which of the possible fractionation mechanisms are actually relevant to this question? Which ones are relevant for the formation of ice sheets? Okay, what processes go on taking water from the ocean to an ice sheet, and how those individual kind of physical processes affect the isotope transfer from the ocean to the ice sheets. Okay, so you can see how you might be able to rewrite questions in a kind of like a simple way like this to identify things that you need to put into your answer. Okay. One thing I should point out at this point, there's a few people made a kind of a horrible error here, and they were writing an answer where it seemed that the description of the formation of an ice sheet was that water in the ocean froze, forming some ice, and that does happen, but that is not how ice sheets form. Okay, that's how sea ice forms. Ice sheets form from water evaporating from the ocean and then falling as rain or as snow over the land, and that like accumulating ice. So it's a very different physical process. You can have isotope fractionations between sea ice and the ocean, but that's not what the question was asking. Okay, so you could have still got marks for the isotope fractionation mechanisms if you had gone down that kind of slightly erroneous route, but again, it's not specifically answering the question, so you'd have missed out on some of the marks. So this is kind of the crux of what we're looking at and what we want to answer. So on the left here, you can see this is a graph showing this is the isotopic composition of the ocean through time. Okay, starting maybe 150,000 years ago to the present, and you can see that the isotopic composition of different ice sheets. This is a Greenland ice sheet. This is an Antarctic ice sheet. There's some variability here, but there's this really big offset between the two. Okay, so there's the isotopic composition is much more enriched in the lighter isotopes, depleted in the heavy isotope in the ice, than it is the water, which is the ultimate source. Okay, so that's what we want to explain, and the physical processes that are going on is that water, okay, in the ocean, that water will evaporate, so there's a process of evaporation, and then that water vapor will condense out as rain, leaving behind some water vapor that's left in the atmosphere, and eventually that will rain out again until eventually all of the water vapor is removed from the atmosphere. But as that water is kind of sequentially kind of removed from the atmosphere, what's left behind gets progressively isotopically light. Okay, so that would have formed maybe the introduction to an answer, but we really want to look at what are the isotope fractionation mechanisms that are associated with these kind of physical processes of evaporation and condensation. Okay, so that's where the main part of the answer is looking at. So there's this idea, first of all, that before we look at the mechanisms of isotope fractionation, there's this process of effectively isotope distillation as we go from the water that's initially evaporated, and then we progressively remove more and more water vapor into condensate, into rain or into snow, leaving behind water vapor in the atmosphere that progressively gets isotopically light. And that can be explained by this kind of Rayleigh distillation kind of process, where we might start out on a diagram like this over here with an isotopic composition that is the same composition that we start with, so a big delta of 0. Okay, so that would be the isotopic composition of the initial evaporated water. So in this case minus 13, so in this case minus 13 minus 13 is 0. It's here. And then when water condenses, the condensate is fractionated from vapor. And in this case, the condensate is isotopically heavier. Okay, so we remove that, and what gets left behind as we progressively remove more and more condensate, the vapor gets progressively more isotopically light as we go down towards this endo here. So when the very, very last bits of water vapor are removed, they are extremely isotopically light. Okay. So you might want to add into your answer why it is that ice sheets are forming from kind of this end of the diagram, and why the rain in this, or the precipitation from this end of the diagram, when it's just evaporated from the ocean, has maybe gone over land a little bit, why that isn't forming the ice sheets. Why is it only the really isotopically light stuff that ends up in the ice sheets? That would have given some extra bonus credit if you'd have gone through and thought about that, but few people did. So the thing we need to look at now are, what are the isotopic fractionation processes? So what is going on? What's causing the isotopic composition of the ocean to be different from the water that's evaporated from that? Okay, so there are a number of options available to us into all of the possible mechanisms of isotope fractionation. There could be equilibrium or kinetic isotope fractionation. And we'll look at equilibrium isotope fractionation first, because that is the most relevant in this case. Okay, because when the water is condensing in these clouds from water vapor into liquid water, there's a continual exchange within the cloud. The water vapor and the cloud droplets are in contact with each other for a long time in the cloud, so isotopes are able to exchange between the water and the vapor phase relatively easily. Okay, so that they're allowed to reach an equilibrium state. And that's almost the case also for evaporation as well from the liquid. Okay, so gas or water vapor can exchange quite readily across the ocean atmosphere interface, but it's not complete equilibrium in this case, because winds tend to blow the water vapor away from the surface ocean. So in some cases we can also have a small kinetic isotope fractionation. We'll come on to that later on. Okay, so you could have just, if this is all that you knew from the, or can remember from the lectures, you could have just said, well, we're going to have kinetic isotope fractionation, and heavier isotopes tend to form stronger bonds, and heavier isotopes are concentrated in phases which have stronger bonds at equilibrium. Okay, and that would have, that level of explanation would have been good. That would have got some marks. You could have gone into a little bit more detail to get yet more marks, as to try and explain why it is that heavier isotopes prefer to go into stronger bonded kind of environments. So if you had two phases, one with a strong bond, one with a weak bond, why is it that the heavier isotopes tend to form, tend to preferentially fractionate into those stronger bonded sites? And that's to do with the vibrational energy of a bond, okay, being related to its the mass of the atoms on the end of that bond. In the very simple case here of a single bond, which can be approximated to a simple spring, that kind of can be explained with these series of equations here. That basically, as the bond vibrates, that's vibrational frequency is equal to kind of this kind of thing here, which has got a term, this mu in here, which is related to the masses of the two atoms. And that's important because that vibrational frequency of the bond determines the energy at basically the energy of the bond. And that's explained kind of with this Planck's relationship here, where the energy at the 0 point energy, or the energy that bond has when it has a temperature of 0 degrees Kelvin, can be related to the vibrational frequency and Planck's constant. Okay, so this is really important because that means that different bonds, this explains why different masses of isotope will form different strength bonds. Backwards. And we can then also see that basically this explains it here, that basically lighter isotopes like a hydrogen-hydrogen, lighter isotopes, hydrogen-hydrogen bond here, will have a slightly higher kind of 0 point energy well than a deuterium-deuterium, so a heavy isotope bond. So they form the stronger bonds. It's harder to get out from the bottom of this well to the top of this well. So the isotopes determine the bond energy. So bonds with heavy isotopes are stronger. And if we look at the situation with water, the water molecule is the same molecule in phase of water and in the phase of gas. So it's not the OH bonds that are responsible for this fractionation, because they're very similar. But in liquid water, there are these additional bonds between oxygen atoms and the hydrogen atoms on other water molecules, these hydrogen bonds. So these add to the overall bonding environment strength in the liquid water phase. So this makes the bonding environment of water slightly stronger. Okay. So we can also think about, are there any kinetic processes going on here? So actually there is a small additional fractionation between the liquid phase and the vapor phase as water evaporates from the ocean, and that is due to that not being an entirely backwards and forwards equilibrium kind of evaporation and condensation, because as the water evaporates from the ocean, some of that water is kind of blown away before it can re-equilibrate with the surface of the ocean. So this means that there are kinetic effects. So there's a faster reaction rate of that evaporation because of the bond strength of the lighter isotopes. So the lighter isotopes will react slightly faster because they have a slightly weaker bonding environment in the water. So that allows them to evaporate faster. Their reaction rate is faster. They are actually moving faster around anyway at any given temperature. So that's another way of explaining how for any given temperature, the lighter isotopes will be moving around faster, because if they have the same energy, they must have a higher velocity, because of that's how kinetic energy works. So those are, again, explanations of how maybe we're having an additional fractionation between the gas, between the water and the initial evaporation. So that can explain this difference. So you can see here on this diagram here that the difference between the ocean and the initial evaporation, the isotopes of the initial evaporated water are lighter by, in this case, 13 per mil. But when that water vapor condenses, the isotope fractionation between that condensate and the precipitation is a little bit less. Okay, so it's a little bit less because the fractionation between vapor and condensate, or water and evaporation in equilibrium isotope fractionation is approximately 10 per mil. So you can see here that we get 10 per mil heavier as we rain stuff out, So our initial fractionation of water is slightly larger because of this additional small kinetic isotope effect. So hopefully that has provided at least, I guess, the bare bones of what should be in that kind of answer. We just kind of flip back to this slide here. So we've identified the processes that go on to form the ice sheet, okay, evaporation, and then sequential condensation, Rayleigh distillation. And we've also gone through and we've identified what are the mechanisms of those individual isotope fractionations. So there's an equilibrium fractionation, which is responsible for most of the isotope fractionation. And that is due to the isotope preferring to be in a more strongly bonded environment. Whereas there is also a small kinetic isotope effect. So really, you could have included the kinetic isotope effect in your answer. That would have been fine. But it would have been a lot better if you'd have included the equilibrium isotope effect, said this is the most important, but there is also a small kinetic effect. Okay, if you'd have only included the kinetic effect in your mechanisms, then that wouldn't really be sufficient to get kind of a huge amount of marks. You'd have got credit for it, but not super amazeballs credit. Okay, so the next question, question 3, which isn't the next question because there was a question 2, but that's not a question about stable isotopes. That's not this video. So anyway. So there's a lot of text that introduces this question. That is not the question. Okay, so basically all as it's saying that we can use boron isotopes to measure, or as a proxy for the pH of a fluid from which carbonates precipitate from. Okay, so the question then goes on to ask, and again in some separate parts, define what's meant by the fractionation factor. Okay. Quite a short answer question that, and then 2 roughly equally weighted. Saying why is there an isotope fractionation between the 2 boron species, okay, and other than pH, what might cause variability in the isotope record that we might produce. Okay, so hopefully you'll realise that the second part, question B, is actually very similar to the first question. So if you'd have done kind of well on the first question and wrote lots about equilibrium isotope fractionation, this would have been a gimme. So first of all, fractionation factor. So this is not a huge amount required for this. So that I think most people kind of got the idea that if in some isotope exchange, if you have 2 phases, CO2 phase and in this example a water phase, you can exchange isotopes between them. And then the fractionation factor is just the ratio in one phase divided by the isotope ratio in the other phase. Okay, so you wouldn't have needed to write out a full isotope exchange equation here, but certainly explaining that the fractionation factor, alpha, if you're going to just write alpha, do define that is the fractionation factor, is the isotope ratio in one phase divided by the isotope ratio in another phase. Okay. You could have maybe given an example that they're actually usually quite close to 1, but that would have been additional and not entirely required. What would have been good is if you'd have thought a little bit more about, I haven't really defined in this question how specifically I'm being about fractionation factors. So this is how we think about fractionation factors, certainly in the case of equilibrium isotope fractionation. But when we're thinking about kinetic isotope fractionation, we can also think about the fractionation factor in a completely different way, in that the fractionation factor, rather than being the ratio in the products, the ratio in the reactants, we can think of it as in the difference in the reaction rates for each individual isotope. Okay, so if this is particularly useful because in kinetic isotope fraction we're often looking at things where we don't maybe have all of the products or the reactants to compare, or we don't take the reaction to completion, so the ratio of isotopes in the product or the doses it can changing through time, so it makes it very impractical to measure an absolute value there. So it may be more appropriate to think about how the isotope fractionates in terms of the difference in the rates of the reaction for each isotope. Okay, and that's kind of what's explained over like this in the lectures. So you could have included that as an additional way of defining the fractionation factor. Okay, that would have given you super bonus marks. Okay, so again, second part of the question, very similar to the question 1. So just why is there an isotope fractionation between the 2 boron species? Okay, so primarily here we're looking at equilibrium isotope fractionation, because when we have these two boron species, they are able to exist in solution in the ocean, so as either as boric acid or borate ion, and there's a constant exchange backwards and forwards between these two species, which means the isotopes can exchange between them very easily. Okay, which means that if these species are dissolved in water, they are very likely to be in isotopic equilibrium. Okay, so your answer to this should really focus on the equilibrium isotope fractionation mechanisms and why they occur. Okay. You might also want to explain a little bit about how these two these two species, are bonded differently. Okay, so we have different coordinations of the boron ion in the middle of these molecules here. So these give different, I guess, bonding strengths, and you can see here that the boric acid, okay, is more strongly bonded, has the higher isotope ratio, has the heavier isotopes preferentially in it, as it were. Okay, so just like with the previous question, this, I guess, slightly more obvious that this question requires a little bit more explanation as to why the isotope fractionate. So why we have these vibrational frequencies which are dependent for each bond, which are dependent on the masses of the isotopes. So these equations for the reduced mass don't really strictly apply in this case, because the vibration of these atom or these bonds cannot really be approximated by a simple spring, but the same kind of basic principle applies in that the frequency is lower when the masses are higher. Okay, so now moving on to the last part of this question, and quite a few people went a little bit wrong with this question, because the question starts out with these three words, other than pH. So when you then go on to write your answer, which explains why pH is a control on the boron isotope ratio, that doesn't answer the question. That is specifically not what the question is asking. Okay, so you need to think about, other than pH, what are the other parameters that can kind of vary in the ocean or vary in the rock record that can affect the boron isotopes preserved in our carbonates? Okay. And other than just writing a list of things that can cause it to go wrong, we can actually write a little bit about what is the mechanisms by which those parameters affect the boron isotopes. And then lastly, what do we have to do to mitigate these additional controls on boron isotopes preserved in carbonates? So really what we're looking at here is this sequence which was presented in the lectures, where the thing that we kind of measure are the isotopes of boron preserved in carbonate, like a shell or a test of some foraminifera or something like that. And there are a bunch of things that can change that. So they're firstly reliant on the boron isotope composition of the ocean, and then there's a pH control, as already mentioned, other than pH. So there is a pH control that affects the boron isotope composition of boric acid, of the borate ion. There is the equilibrium constants for the dissociation of that boric acid. There's the isotope fractionation factor between boric acid and the boric ion. And all of those things can change the isotopic composition of the borate ion. And then that has to then get into the carbonate. So there's a isotope fractionation between the dissolved boron in the borate ion and in carbonate. And there's this, is that exchange actually in equilibrium? So this over on the right here is what quite a lot of you kind of like started to write about, but this was not what you should be writing about. Okay, so this is why boron is, the isotopes of boron are pH dependent. Okay, so there's a speciation between the two forms of boron in the ocean, boric acid and the borate ion, and the relative proportions of those is dependent on pH, because there's a hydrogen ion associated with that dissociation reaction. So that's kind of shown in this graph here. So at low pH we have more of the boric acid, and at high pH we have more of the borate ion. And then there is a isotopic fractionation between those two species because of the answer to the previous question, why is there an isotope fractionation between the two boron species? Because their bonding environments are different. And then you get this pH dependency, which is this horrible reaction at the bottom, which I'm really hoping is too small for anybody to read, because that's not what the question was about. Okay. So what the question about was really going through each of these things that are in this series of kind of parameters that control how boron gets into the thing we're measuring and what controls that. So I guess first of all is the total isotopic composition of the ocean. So if you change that, then you will change this over here. Now, you could have said that would have been great. It would have been also nice if you'd have mentioned that the residence time of boron in the ocean is quite long, a couple of billion years. So that means that it's not going to change much over the time periods we're using boron isotopes as a proxy. Over long time periods, tens of millions of years, then yeah, we might have to worry about changes in the ocean content of boron. So that doesn't really change through time along most of the timescales we're interested in, but it's important to mention that if it did change, that would change our answer. Next things other than pH are the equilibrium constant of the boric acid dissociation and the fractionation factor of of the boron isotopes between the two boron species. Now, it's a fractionation factor. That fractionation is due to equilibrium isotope fractionation, so you should know that that must have some temperature dependence on it. The equilibrium constant of the chemical exchange certainly does have a temperature dependence on it, so that was explained in these kind of plots that we saw here. And not only is there a temperature dependence, but there's also an effect of salinity and pressure. So these are all things that you need to have effectively noted down, that all of these things can affect these parameters here, which will then in turn affect the boron isotope composition of the dissolved borate ion. So moving on to the things taking this borate ion into the carbonate phase, again there will be an effect of temperature because it's a fractionation factor. Okay, so just like with the fractionation between the two boron species, the fractionation between the borate ion and the carbonate bound boron will have some temperature dependence on it. Okay, and is it in isotopic equilibrium? Okay, so this is the idea that the isotopes or the atoms, individual atoms of boron, aren't really exchanging between seawater and the kind of carbonate bound boron, because once they're in the carbonate bound boron, they're bound in the carbonate and they can't exchange again. And actually, during the formation of kind of biogenic carbonates, the seawater, which is kind of in these diagrams here, isn't really in contact with the thing that's actually doing the precipitation of the minerals. Okay, there's some kind of cell in the way. Okay, so they're not truly going to be in isotopic equilibrium. Okay, so the idea that there is some equilibrium isotopic fraction base between these two isn't quite true. So how do we get round these problems? Okay, so this is moving on to maybe the last part of this question here. We use empirical calibrations where we measure the carbonate-bound boron isotopes and compare that with what we should be getting for the borate ion. Where have we gone? Borate ion, boron isotopes, and you can see that we don't fall on the one-to-one line for many kinds of sample, but that doesn't matter because if we can produce our own calibration curve, we can use that to kind of effectively correct for this non-equilibrium effect, or sometimes called the vital effect of biology kind of messing things around a little bit. So that kind of gets us back, those empirical calibrations get us back to here, the composition of the borate, the isotopes of the borate ion, but really to get back to the pH, if that's the thing we want to know, we still have to worry about these other effects, and these are largely due to temperature, so we would need to measure another temperature proxy, maybe magnesium calcium or strontium calcium or oxygen isotopes or alkanones, something that gives us an estimate of past sea surface temperature, or at least the seawater temperature in which that carbonate was precipitated in. So that's one of the things that we have to do. Okay, so we have to do empirical calibrations to get back from this step and to get to this step back here. We assume that this doesn't change, and we make some accounting for the temperature dependence by measuring another proxy for temperature. Okay, so hopefully this series of kind of going over the questions has helped you identify the things that you kind of should have known for these questions, would have given you some better idea about how your answers could have been structured, or how you could have at least looked at the questions and maybe identified a little bit better about what that question was actually asking you. Okay, so here's a pretty picture to end the video. I'm sorry to get rid of me. Okay, so hopefully this has been useful. This is the moon, I think, which is pretty exciting, and the chemistry of it, which is totally irrelevant, but it is a nice image to end on. So I hope you found this useful. If you've not, then I guess if you want more feedback on the exam, come and find me, or come to the exam feedback session, which will no doubt be run this semester sometime, and we can talk, and it will be fun, and we'll all enjoy it.